Today's lesson is going to center around perpendicular vectors, vectors at a 90-degree angle. And here's a vector A and B, and they're perpendicular. And if you notice this notation right here, that little dot right there is known as the inner product. Okay, and the inner product, well, actually here, vectors are perpendicular when their inner product equals 0. Okay, so this is the notation for the inner product. There's inner product. And when it equals 0, vectors are perpendicular. It conveniently goes by another name as well. You'll also hear it called the dot product. And since it looks like a dot, that's pretty easy to remember. Inner product or dot product, they're synonymous. All right, let's do an example. Well, here, how do we figure that out? Let me give you that much. So, in the xy plane, okay, if we just have a two-dimensional vector, then if we're given vector A, that's 1, and vector B, call that x2, y2, well then, the dot product or the inner product of A and B equals this. You multiply the x values and you multiply the y values. Pretty straightforward. Alright, well, let's try it. This example right here. Okay. Pixels aren't that good. Here, let me do this. Let us pretend that these two are meeting at the origin. Okay? And these are the x and y components. This one has a negative 12 and a 16. This one has a 12 and a 9. I am going to make this a negative 12 because that is what it is. We're doing the xy coordinate. Well, let's figure this one out. We would have, well, this would be x1, y1, and x2, y2, and because we are multiplying, they're commutative. It doesn't really matter which one comes first or second. Well, let's do the math here. So that would give us negative 12 times negative 12, times positive 12. And I'm going to add to that positive 12 times 9. And that's going to give us a negative 144. And hold on. It would help if I used the right numbers. Oh, I can't erase that, huh? Okay. Well, I should have put a 16 here. We're multiplying the y values over here, so I have 16 times 9, okay, and then negative 12 and 12 are the x values. All right, let's continue. You multiply 16 times 9, that will give you a positive 144. And you add the two of these up and you get a 0. Okay? Since these inner products or the dot product of these two vectors is 0, they are guaranteed to be perpendicular, just like it shows here in the diagram. And so what if we are in three-dimensional space? Well, very little changes. Just like before the other day, we just have the z component to deal with as well. So let's see what we got going there. Okay, I'll leave that up there in case you need to copy that down. And, well, that's a pretty picture, but I guess we're done with it. Here's what I want to focus on over here. This is what the formula for the inner product or the dot product is in when you're in a plane. Just x and y. And here, when you're in space. That just means we have the z component as well. Okay? Well, it looks the same. It just has z1 times z2 as well. So it looks like this. Plus z1 times z2. And if that equals 0, then whatever two vectors you're dealing with are perpendicular. Let's do an example. What if we're given vector A, 5, 2, 7. And vector B, 3, -4, -1. And we are asked to find the inner product. Or we could just be asked, are they perpendicular? Well, we're still going to use this, because if we know what the inner product is, we know what's going on if they're perpendicular or not. Let's continue. So, oops, hang on. Green. The dot product of A and B, and again, I'm not out to confuse you, but I just want to make sure you see all the different symbols for vectors. Okay, could look like this, could look like this. And the one like this I've been using, all three of them are good to go. Well, you take your x and you multiply them, so we have 5 times 3. Plus, we take our y values, which is a 2 times a -4. And we are going to do the same thing with our z values, 7 times -1. Let's see what we get. 15, -8, -7. That is 0. The inner product is 0. These two vectors are perpendicular. As a gentle reminder, if you don't recall the symbol for perpendicular, that is it. And we could state then that vector A is perpendicular to vector B. Okay? Just to refresh your memory on the notation there. Now for the cross product of vectors. First, what is it? Before we find it, let's figure out what it is we're finding. Couldn't really decide which picture I wanted to use, so those are the two I was deciding on. Anywho, we are going to find, so we find two vectors that are perpendicular. We find vector A and vector B are perpendicular, and let me just draw it in there. Let's say that this theta here, they are probably my worst one ever. Anyway, that's not that big. So anyway, if we find two perpendicular vectors there, the cross product of these two is guaranteed to be perpendicular to both of them. So it's going to be perpendicular like that, and coming out this way. Let me do it in a different color, green. And also coming out this way, perpendicular with A, and over there the orange one perpendicular with B. And there's reasons we find that. Again, these things represent force, like we were mentioning. And this cross product, well, we'll talk about that a little bit further, a little bit deeper in the next couple lessons. But here's how we find it. I guess I'll just... whatever. Make things... there we go. Just need a little more room. Well, if we are given... Hang on, let me do this. If we are given vector A, and vector A is x1, y1, z1, and vector B is, you guessed it, and commas, I guess, would be appropriate. Okay, so then the way you find the cross product, now I know that I've said in the past that anything we've done in the first half of the year will not show up in the second half of the year, except for this. All right, I lied. One little topic. We are going to go back to matrices, and if you remember how to find the determinant using cofactors, that's what we're going to do. We're going to set up our 3 by 3 determinant as such. Our first row is going to be the unit vectors. Okay, so like in the matrix unit, we're going to have a x column here and a y column here and a z column here, and the unit vectors for those axes go on top. Next, we have our A vector, which is x1, y1, z1, and our B vector, which is x2, y2, z2. Actually, it just dawned on me. Before I continue with the cross product here, let me revisit something over here that we talked about. I just told you theta's 90 degrees. That does not have to be true. This theta here, it really makes no difference. That could be any, I mean, even if it's just a 30 degree, a little acute angle, you could still find the cross product. That can still be perpendicular with the two vectors. So scratch that. Perpendicular here, perpendicular there. It does not have to be perpendicular at that theta. Okay, let's continue. Equals that. We have the cross product of AB equals. We take the first column, which is I, J, K. And then we cross off the row in the column with I, and we're left with a little 2x2 determinant. That goes here. So, in this case, it would be Y. I gotta make this smaller. Hold on. So we're gonna have Y1, Z1, and Y2, Z2. Okay, and that's Y1 right there. And then for the J, we cross off the row and the column with J, and we're left with these four, the ones I just circled. So that would be an X1 and a Z1 and a X2 and a Z2. And for the K, we repeat the process. We cross out the row and the column with K, and we are going to be left with these four right here. Okay? Because if we cross out that row and that column, we get those four, which is, let me go back so it's easier to see. That would be X1, Y1, X2, Y2. Great. Now, don't forget, it's also a positive whatever that value is, negative whatever that value is, and positive whatever value that is. Okay, so now let's figure it out for a couple of vectors. Say we are given vector A has coordinates 5, 2, 3. And vector B has coordinates of a negative 2, 5, 0. And we want to know the vector that would be perpendicular to both of them. Okay, the cross product. Here's how we find it. The cross product, actually let me write it up here and then we'll expand it over there. We have the cross product is going to look like this. We have the unit vectors on top. We have vector A, which is 5, 2, 3. And then vector B, which is negative 2, 5, 0. We're going to find the determinant of that. Now we need to do this by hand because, well, how are you going to plug in I, J, K into your calculator? Good luck. So here we go. We're going to take the first row, which is I, J, K. And we're going to figure out the 2x2 determinant. I don't want to make a mess of this, so we're going to have these four, and I just made a mess of it. Undo. Oh, I can't even do that. Well, I just messed it up. Let's go back to the green I was working in, and we have 2, 3, 5, 0. And next, for the J, we are going to have a 5 and a negative 2, and a 3 and a 0. I'm hoping that this is ringing a bell. We've done this enough earlier in the year. And then for the K, we cross the row and the column out, and we have a 5 and a 2 right here, and we have a negative 2 and a 5. It is positive I, negative J, positive K. And technically these are vectors as well, so boom. And let's figure this out. So I have a lot of green going on, so here is I, and how do we figure this one out? It is the product of these, which is 2 times 0, which is 0, minus the other product, this product right here. So 5 times 3 is 15. And then we have negative J. This is 5 times 0 is 0, minus a negative 6. Plus k times 5 times 5 is 25 minus a negative 4. That's going to give us a negative 15i. And what do we get here? We get positive 6. 0 plus 6 is 6. But 6 times a negative j is a negative 6j. Here we have 25 plus 4, which is 29. So that's a positive 29k. Does that look familiar? It should. It is the sum of unit vectors. Ta-da! So that would be written as the sum of unit vectors and if we wanted to write it as an ordered triple, okay, an ordered triple, hang on one second, let me do this. And I guess we'll do that too. And back to this. Ordered triple. It is 3 numbers in a certain order, an ordered triple. That would be written as negative 15, comma, negative 6, comma, 29. There you have it. Now be mindful, sometimes the question is going to ask you to write it as the sum of unit vectors. Sometimes it will ask you to write it as an ordered triple. Provide your answer in the right format. Now this word is not always brought up at the high school level, but I just love the word. It's just so fun to say. Orthogonal. Orthogonal. And it's really what we're talking about. These are orthogonal vectors. They meet at a 90-degree angle. So, you know, if you're going into college, if you take any math course in college that's going to be dealing with anything perpendicular, it wouldn't surprise me. You know, I'd be surprised if you didn't hear the word at that point. But anyway, orthogonal. It's things that are lying or intersecting at right angles. So there you have it. Something else you learned. These are the unit vectors, and they are all orthogonal. This is perpendicular to that one, and this is perpendicular to that one, and this one is perpendicular to that one. They're all orthogonal. And while we're at it, it looks to me, well, let's see here. I have a vector and a vector, and since y is perpendicular to both of them, y must be the cross product of x and z. Oh, and no kidding. X is the cross product of y and z, and it looks to me like z is the cross product of x or y and x. No kidding. How about a quick little recap? Say we were given vector A and vector B, and we were asked to find the inner product, also known as the dot product, and we come up with a value of 0. That guarantees that these two vectors, A and B, which can also be notated like this, are perpendicular with one another. That's a B. Alright, what about the other one? The cross product. If I take the cross product of these two vectors, well, unlike here, this gives you a numeric value. This one gives you another vector. And this vector is guaranteed to be perpendicular not only to one of them, but to both of them. And we saw a diagram before like this. If we had a vector A and a vector B over here, it's guaranteed, here, let me just change the color. It's guaranteed to be not only perpendicular to with that one, but also this one over here coming out. Pretty cool. Please pause for a moment if you need to. Or rewind and listen to it again, for that matter. Alright, before we all close up our notebooks, let's get the assignment in there so when you get into class you can just get going on it. We did perpendicular vectors, and the assignment associated with that is this one right here, page 433. So, in class tomorrow, we will be doing page 433, those problems. See you there.